All right, this is going to go through again, today 5-1 warm-up, and I'll go over the homework, and then 5-2 notes. So starting with the warm-up, remember we needed like that little reference sheet. Everything that was on the reference sheet needs to get into your brain, okay? The reciprocal functions, the co-functions, the even-odd functions, and the Pythagorean identities. All that stuff is stuff you need to know for yesterday, and the good thing is for today, we're going to review it again today. So number one, to just simplify the given expression, 2 sets of parentheses, what would you normally do there? Distribute. So if I FOIL that out, I end up with secant squared x plus secant x minus secant x minus 1. And then these two cancel, and I get secant squared x minus 1. Good. So this is one of your identities. Remember, your Pythagorean identities would be sine squared plus cosine squared equals 1. And then tangent squared plus 1 equals equals secant squared. And then 1 plus cosecant squared equals cotangent squared. So this is my secant squared minus 1, which means I'm taking the second one, subtracting 1 from the left and the right side, which just leaves you with tangent squared. Number 2, now I've got secant squared x times 1 minus sine squared x. So I would say there's a couple different ways to do this. What's one way you could do it? Good. That's probably the easiest way to do it. Take this, replace it with your cosine squared x. And then secant's the same thing as what? Good. Times cosine squared x, and then they cancel, and I just get 1. Anybody do it differently? How'd you do it? Distributed them. Mm-hmm.
And then distributed to both. And I got secant squared of x minus sine squared of x times 1 over cosine squared of x.
Okay.
And then changed into secant squared of x minus tangent squared of x. And then I put them both as like 1 over cosine squared of x. Sine squared of x over cosine squared of x.
Oh, you went further. You wrote it like this?
Yeah.
Okay. You said 1 over cosine, or you made that sine over cosine?
Yeah, 1 over cosine, and then sine squared of x over cosine squared of x.
Gotcha.
And then I put them over the same denominator.
Okay.
So I changed the 1 minus sine squared of x to cosine as 1.
Gotcha. And then cosine squared over cosine squared, that works, which equals 1. You could have gone from here too, right? Like secant minus 1 if you use that trig function. If I had subtracted secant minus tangent, I also would have gotten 1 there. So there's a lot of different ways you could do that one.
Oh, wow.
Yeah. It still works. Don't, like it's not the fastest, right? Not the quickest. Yes, it will help you on time for your test, but it doesn't mean it's wrong if it takes you a couple extra steps. All right, how about the last one? Secant x over cosecant x minus tangent over cotangent. Alex, what'd you do?
So I turned secant x into 1 over cosine x, and then I moved the cosine x to the top to cancel them out to equal 1. And then for the right side.
So wait, I'm gonna stop you there because that would be, right, when I do keep, change, flip, it would look like that.
Oh.
So that would be 1 over cosine squared x, right? And then what'd you do on the right?
I turned the tan into sine over cosine, and then the cotangent into cosine over sine, and then cross multiply it to get sine squared of x over cosine squared of x.
So when you flip it, so keep, change, flip there. Okay. And then you're here. And then combine them together?
Yeah.
And then 1 minus sine squared is, right, cosine squared. Is that what you did?
Yeah.
And then that's 1. Sophia.
Wait, so when you simplify the secant x over cosine x, why wouldn't it give you 1? Because then you have to like keep change flip.
So it's 1 over cosine. It ends up so that the top would be 1 over cosine, right?
Yeah, so like so secant would be 1
Over cosine, and then when you
times
keep change
cosine.
flip, it becomes
Cosine.
times 1 over cosine. You're dividing by cosine over 1, which means you multiply times 1 over cosine.
Oh, okay.
Yeah. Anybody do it differently?
Well, I had a question.
Okay.
I was kind of wondering this in the homework last night too. If you ever, like, especially with these, with the fractions, if you see tangent or any of the reciprocal functions, do you always want to change it to like sine and cosine?
Probably.
Okay.
Yeah, probably. Unless you see tangent and cotangent, like maybe you want to make them one,
Well,
like.
yeah.
But typically, if tangent's in there by itself, unless it's squared and I can use one of the Pythagorean
Okay,
identities,
that's what I was asking.
I change it to sine and to
Okay.
cosine. Yep. 1.
So once you get, like I got the cosines, 1 over cosine squared of x, and I changed it to secant squared of x.
Uh-huh.
And then,
Minus tangent squared of x. Do you have that?
and that's 1, 2.
Yep. So I could, from here, you could have made that secant squared of x minus tangent squared of x, and that's 1. There's one other way that's super fast. Yesterday I told you that if you could separate out the terms and there's denominators, you can move them, right? Do you remember this? Did anybody do that?
So wait, what you're saying is that if you move cosine of x up, it would have become secant.
Exactly.
times
So I'd get
secant
secant x times secant x, or secant squared x. So if you move it to the top, it becomes its reciprocal function, which means if I move cotangent to the top, it becomes what?
minus tangent. Well, it becomes tangent squared x.
Good.
And that gives you 1.
And that's 1.
And I just noticed.
Can you say that again?
Yep. So when your fractions have single terms, okay, so there's nothing adding or subtracting from the cosine or the cotangent on the bottom. When they are like that, you can move them to the top by making them the reciprocal functions. It's a shortcut. You're basically doing divided by that function, which is multiplying by the reciprocal, and the reciprocal is secant. So it's the same idea, except you're just moving it. When you move a term from the top to the bottom or the bottom to the top, it becomes its reciprocal function. So if I take cosine and I move it to the top, it becomes secant, and I would have gotten secant times secant, which is secant squared. If I take cotangent and I move it to the top, it becomes tangent, and then I get tangent times tangent, which is tangent squared. And if you go back to your identities at the top, if you go back again to the top, the tangent and the secant one, if I move tangent to the other side so that it is secant minus tangent, it becomes 1. So they are all right, okay? Those 3 or 4 different ways that you mentioned were all right, okay? It doesn't make them any more right that it's shorter. It just makes it quicker for your test, okay, and easier. So just think about moving stuff, especially if it's fractions like that. So I think the instructions even told you to factor it, right? Yeah. So I would have replaced sine squared this time with a, which means this would have been 1 minus 2a plus a squared. And then I would have reordered it so that the highest exponent comes first, and then I would have factored it out. So that's an a minus 1 and an a minus 1. Or a minus 1 squared. And then a itself was sine squared. So I would get sine squared x minus 1 squared. And because sine squared plus cosine squared is 1, sine squared minus 1 would be cosine squared.
That's the same thing as 1 minus sine squared.
No, it would be different because sine squared plus cosine squared. That actually should have been negative. So I would have gotten sine squared minus 1 equals negative cosine squared, right? So this would be negative cosine squared, but cosine is an even function, which means that negative can go back positive, or you're squaring it. Either way, it would go back positive because it's squared. So negative cancels out, and then cosine squared squared would be cosine to the 4th.
Like, I remember one time you did like sine squared of x minus 1. If you like multiply them, you did like 2 sine squared of x minus 1. And you not do that.
You mean like once you're in the bottom? Yeah, but you have to then replace. So you could expand that out, but it becomes less simplified. You mean take sine squared x minus 1 and multiply it times sine squared x minus 1?
Yeah.
So like you're working the other way. So we're trying to factor it out, which means we're trying to make it into like a, instead of the other way around. Does that make sense? Directions on that would say multiply it out.
What is the sine squared, sine to the fourth?
What happens if it's sine to the fourth?
Yeah, like, it's, I think it's in the question.
Say that again.
That, what happens to the sine to the fourth? Like, how,
So that's not the original question?
yeah, like, yeah, in the original.
Oh, I replaced that. So when you, so I replaced the sign, like I always look at the middle term, right?
Yeah.
That's what I want to replace with A.
Okay.
And it's just like saying 1 minus 2x squared plus x to the fourth is kind of like what's happening there. So then when you factor it out, it would have been x squared instead of x to the first on that first term. That's all. But I take out that part, put in the A, and then bring it back in at the end.
Okay.
So instead of just bringing in the sine, we actually brought in a sine squared. And then that's raised to the second power, which makes it to the fourth. All right, so this, was it under the factoring instructions or did it just say simplify? It did say factor, okay? Even if it didn't, hopefully you start catching like greatest common factors with things you can take out. So in this one, you've got a cotangent on both. If I factor out the cotangent squared, then I get 1 minus cosine squared. And then 1 minus cosine squared is sine squared. Cotangent is cosine squared over sine squared times sine squared. And then I can cancel through these, and I'm left with just cosine squared. Christian?
What's the difference between factoring and simplifying?
It would be the same. It's just that it's actually like telling you how to simplify it. So if that question appears on your test, it actually just might say simplify. And you'd have to know factoring is one way you could do it. It's just basically helping you out by telling you what to do. All right, and then, so 52 is also a factoring question, but if it wasn't, I would look at those as those there are the difference of two squares, right? They're both perfect squares and there's a minus between them. So when you factor it out, the square root of secant to the fourth would just be secant squared. And then the square root of tangent to the fourth would be tangent squared. One's a plus and one's a minus. So as soon as I see the squares and the secant and the tangent, I would know that tangent squared plus 1 equals secant squared. So in order to get the secant and the tangent on the same side, I'd have to subtract the tangent from the left. And I get 1 equals secant squared minus tangent squared. And that's the one I can replace. So the other one would stay how it is. The plus can't get replaced with anything. And then that would be 1, which means just leave it how it is, which is the plus. And that's as far as you can go. So you can replace a minus, a secant, a tangent minus a secant, or a secant minus a tangent, but you can't replace a secant plus a tangent. The good thing is everything you already know is what you need for 5.2. There's absolutely no new identities that you need to know. Okay, the same reference sheet is what you need to be memorizing. All the reciprocal identities, the Pythagorean identities, the even and odd, and the cofunctions all get reused. And in my opinion, this one's even easier because they give you an end goal. Because you get a left side equals a right side, and your job is to get that left side to equal right side. So here's some guidelines, because again, I can't tell you that step 1 is this, step 2 is this, step, because they're all different, okay? So you want to start to get familiar with these by trying as many as you possibly can. That's, to be honest, the easiest way. But basically the idea is on the top. It says work with each side of the equation independently of the other side. So you can either start by working the left side to make it look like the right side, or the right side to make it look like the left side. You might even get to a point in which you have to work both sides. And it doesn't matter. As long as your answer at the end is a balanced equation, meaning the left side equals what's there on the right side, then it doesn't matter if you have changed the left side or the right side, as long as it's balanced. But this one just gives you like the pointer of start with the more complicated side, okay? If I only have sine on the left-hand side, I can't change sine to be anything that's more simple than sine. So I'm probably going to work the right-hand side, or vice versa. Then it says analyze the identity and look for opportunities to apply the fundamental identities. So if you see something, where it's a function that is squared with another squared function, you're probably looking at the Pythagorean identities. or a function that's squared with a 1, you're probably looking at your Pythagorean identities. If you see your cofunctions, like pi over 2 minus an angle, then you're looking for your cofunctions. If you see a negative on the x, you're probably looking at your even and odd functions. You've just got to become familiar with them enough to be able to spot it. And then it says you try using one or more of the following techniques. So obviously, write the more complicated side in terms of sine and cosine. Work that more complicated side. If you see a greatest common factor, factor it out. If you've got fractions, so if it starts as a fraction in which the numerator has 2 terms, split them. It's going to make it easier. Same thing here. If it's a minus, still split them, but put the minus in between. And then if it's the other way around, if you're dealing with something like a over c plus b over c, you want to combine them into one fraction. And then the last thing says multiply the numerator and the denominator by a binomial factor that appears on the other side of the identity. So this happens if you get like a cross multiplication. So if I said sine of x, I'm just making stuff up, over, I don't know, tangent of x. This is not right at all. Just bear with me. If I have one parentheses on either side, or one fraction on either side of the equal sign, then I can cross multiply. So sometimes it's easier to do that. And then on the bottom is a really important point. Don't be afraid to stop and start over again. If you hit a dead end and you are totally stuck, try it a different way. Okay? It doesn't mean you're wrong. Sometimes we think one way and it's not going to get us to the right answer. And then sometimes we get really lucky. All right, so we're going to work through as many of these as we can. So I'll verify the identity. Look at the left side, look at the right side. Which one is more complicated? The left side. So I'm probably going to start there. There's some squareds in there, so that would be my first indication to go to my Pythagorean identities, which say sine squared plus cosine squared equals 1, tangent squared plus 1 equals secant squared, and 1 plus cotangent squared equals cosecant squared. Yeah, there's technically an x or a theta or anything, right? I just, to remind you, like, to write it out. I'm not going to mark you wrong on what you, as long as you know how to use it. So what do we see in this that we could use? Bradley?
Cosine squared x and cosine squared x gives you 1.
Good. So then I get cotangent squared x plus 1 equals cosecant squared x. We see anything else we could use?
Where do you go from there?
Look at this one, right? So we needed 2 Pythagorean identities to get us through it, but that's all we needed. 1 plus cotangent squared would be the same thing as cotangent squared plus 1, which is cosecant squared.
Can you say that again?
1 plus cotangent squared. So up here I have 1 plus cotangent squared, right?
Yeah.
But where we are, we have cotangent squared plus 1. They're the same thing. The order on the addition doesn't matter. So pretty basic, right? We needed 2 Pythagorean identities to get us there, but that was it. Okay, example 2, tangent squared minus sine squared equals tangent squared times sine squared. I've got squareds, right? But sine and tangent are not in the same Pythagorean identity, right? What goes with tangent? Secant, right? It's an S, but it's the wrong S, right? So I'm going to rule that one out, and I'm going to think, okay, I've got to do something else with my squareds. Okay? This time, they're kind of both on the same level of complexity, but the left side does have 2 separate ones that I can rewrite into fraction form, right? So what would be tangent squared if I rewrote it in fraction form? Sine squared over cosine squared.
Wait, the x doesn't carry down. Huh?
Yep, it does. Sine squared x over cosine squared x. I'm gonna work the left side for a little bit and see if I can get anywhere. Now, in order to get 2 fractions to 1, I've got to give sine, oh, this should be sine squared over 1, the same denominator as the one on the left, which means I have to multiply both the top and the bottom here by cosine squared x. that's really hard to read, sorry.
If you use the same denominator, so she multiplies by cosine squared. You can't really see what that.
Yeah, I just realized that. I'm going to read it. So now they've got the same denominator. I can combine them. So I get sine squared x minus sine squared x cosine over cosine. Can I do anything from there? I can take out the sine squared. Now what?
Wait, how do you take it out? You just factored it out.
Mm-hmm.
You have cosine squared over cosine squared, which is 1.
So I have 1 minus cosine squared. That is an actual thing. I can't break that up.
Isn't that the same thing as sine squared?
Good. That's a Pythagorean identity, right?
Sine squared.
So this becomes sine squared. So now I've got sine squared.
You put sine for x.
Yep.
Wait, so this is all the left side?
This is still the left side.
Okay.
So I'm at a place right now where if you compare them, there's actually 2 ways that I could work this, like equals tan. So I can separate those 2 out because it's multiplication. If that said sine squared x plus sine squared x, then I would have had to put them both over cosine. But because it's multiplication, I can split them up. So then sine squared over cosine becomes tangent squared times sine squared. And this. And now the left side equals the right side. They're so deceiving, right? Like when you look at that beginning question, it looks like, oh, the left side has the plus and the right side it doesn't. That's it. Sometimes they're a little bit more deceiving. I could have also worked the right side from this step. So if from here you wanted to replace tangent with sine squared over cosine squared and then multiplied it and got sine to the 4th over cosine and the left side sine to the 4th over cosine, you still have a balanced equation. So you could have done it that way as well. Sometimes you do have to work both sides. You don't get the option to only work one. Sophia?
So your final answer doesn't have to be the same as the original right side?
Nope, as long as it's balanced. Sometimes you're going to have to move both.
How do you know if it's balanced?
Say again?
What makes it balanced?
Like the left side is exactly equal to the right side.
So what I did is that I put sine over 1 over sine
Okay.
plus cosine x over 1 over cosine x.
So sine x over 1 over sine plus cosine over 1 over cosine. Okay.
Yeah, is equal to sine multiplied by 1 over sine.
Okay.
Keep change up on both of them. You have sine squared x plus cosine squared x is equal to sine x over sine x, which is just 1.
Okay.
And then by the trigonometric identities, 1 is equal to 1.
Nicely done.
Do we
Okay.
have to write the one equals to 1?
No, remember you can skip. This is your shortcut. So if you bring it to the top, it becomes sine. Bring this to the top, it becomes cosine. Sine squared plus cosine squared. But then you get there and there's nothing you can do once you get to 1 equals sine x of cosecant x, which means you then have to work the right-hand side. Okay? So again, sometimes you're going to have to work both sides.
I thought if you worked on one side, you can't touch the other side.
You can balance. I mean, the whole goal is to get to a balanced equation at the end. So sometimes you got to work both. And you can even bring stuff over. Like I could divide both sides by sine. And then I end up with 1 over sine on the left and cosecant on the right, and I end up with cosecant and cosecant.
So you just simplify it as you can.
Until the left side equals the right side.
So it has to be like the same things on each side.
Exactly.
Okay.
Yep.
The second to last step, is that okay if we write that for our answer as well?
No.
We have to write
So
the one
your
equals
ending answer has to be
1 equals 1.
identical on either side of the equal sign. That's a good question. Yes, I know that's 1, but you have to show me that you know that that's 1. Alex.
For this problem, you could bring the cosecant to the top.
Yep.
Is that what you did?
Yep. Well, he did the 1 over and then did that, but you can just bring it. Yeah. Okay, let's see if we can get one more in. So this is cotangent x times 1 plus tangent squared x over tangent x equals cosecant squared x. So what do you see there that immediately you could replace? 1 plus tangent squared is what? Secant squared. So I get cotangent x times secant squared x over tangent x equals cosecant squared x. Okay, now what? You can bring, okay, so you're both, all of you are right. You can split it so that it's cotangent over tangent, or you can bring it to the top. Either way, if I bring tangent to the top, it becomes what? Cotangent, so I end up with cotangent squared x times secant squared x. Cotangent is cosine over sine, and secant is 1 over cosine. So the cosines cancel out. I get 1 over sine squared, which is cosecant squared, right? That's okay. Equals, bring it down. Oops. Cosecant squared x. 1. So this is one I would say that it's probably not the worst thing in the world to cross multiply. Okay, you've got one fraction on either side of the equal sign. If I cross multiply, I get sine of x times 1 plus tangent of x equals tangent of x times sine of x plus cosine of x. And then distribute, so I get sine of x plus sine x tangent x equals tangent x sine x plus tangent x cosine x. Now what? You see something on either side of the equal sign that are the same? These are both the same, right? Whether the order is different or it's multiplication, they're the same, right? So I can actually subtract and these cancel, and I get sine of x equals tangent of x times cosine of x. And then tangent becomes sine over cosine times cosine. Those cancel, and I get sine of x equals sine of x. So depending on what it looks like, there's going to be different strategies to start. You just got to figure out, you know, like what works. And it doesn't mean that's the only way. And it doesn't mean you might have stopped and, like I said, started and hit a wall, but you got to retry them again. Don't ever leave these questions blank, even on homework. Like a question mark on homework does not fly with me on this stuff. You got to at least try it. You got to at least be able to replace some part of it. Doesn't mean you can't get 5 steps down and get frustrated and put a question mark. That's different. Okay? But you got to at least start it. They're like geometric proofs. You got to give me at least something. I could have said sine over cosine, right? Like sine x over cosine x over 1 plus sine of x over cosine x. And then made this cosine over cosine. So I get sine of x over cosine of x over 1 plus, no, sorry, not 1. Cosine x plus sine x over cosine of x. And then I can do keep, change, flip. Those cancel, and I end up with sine of x over cosine of x plus sine of x, which is the same, just the order is different, but you could definitely do it that way. I tend to just, like, if there is one fraction on either side, a lot of times cross multiplying is easier, okay? But it doesn't mean it's the only way, for sure. That's the thing about this is, like, you might get 2 totally different mapped out plans, but if you have a balanced equation at the end, it doesn't mean that it's wrong. And that also means you have to show your work on these. Like, I know what it's supposed to look like at the end. It gave it to you at the beginning, but you have to show me all those steps in between.